Every second, billions of messages cross the planet. A video call from New York to London, a bank transfer from Dubai to Singapore, a TikTok upload from Istanbul, a cloud file opened in Tokyo. An AI model answers a question from somewhere thousands of kilometers away. It feels instant, invisible, and wireless, but the truth is far more physical than most people imagine. The global internet is not really floating through the air. It is lying at the bottom of the ocean, under waves, storms, shipping lanes, fishing zones, and military patrols. There is a hidden maze of fiber-optic cables connecting continents together. These cables carry the world's emails, payments, videos, financial trades, cloud data, and almost everything that makes modern life feel connected. And this creates a strange paradox. The internet feels like one of the most advanced systems humans have ever built, but much of it depends on physical cables resting in some of the most difficult places on Earth. So the real question is not just how the world stays connected. The real question is how fragile that connection really is. When people imagine the internet, they often imagine satellites, cell towers, Wi-Fi signals, and data floating invisibly through the air. That makes sense, because we experience the internet wirelessly. Our phones connect without cables, our laptops connect without cables, and our smart TVs stream without cables. But that is only the last step. Your phone may connect to a nearby cell tower, and your laptop may connect to a router. But once your data needs to cross an ocean, the story changes. It usually does not go through space. It goes under the sea. Satellites are important, especially for remote areas, ships, aircraft, emergency backup, and places without strong terrestrial networks. But for high-volume global internet traffic, satellites are not the main highway. They are more like special routes. The real highways are made of glass fibers crossing the ocean floor. Fiber is fast, high capacity, and efficient. A single modern cable can carry enormous amounts of data using pulses of light. That data travels through hair-thin strands of glass, boosted by repeaters along the route. The internet may feel weightless, but it has a body, and that body is made of cable. But here is where the story gets more interesting. These cables do not just connect countries. They quietly decide which countries become faster, richer, more competitive, and more connected. If you could drain the oceans and look at the seabed, you would see one of the most important maps on Earth. Not a map of borders and not a map of armies. A map of cables. These routes stretch from North America to Europe, from Europe to Africa, from the Middle East to Asia, from Asia to the United States, and across the Pacific, Atlantic, Indian Ocean, Mediterranean, Red Sea, and beyond. Each landing point is a place where the digital ocean meets land. A landing point might be a beach, a coastal city, a secured facility, or a building that most people pass without noticing. Inside that landing station, the cable connects to terrestrial networks, data centers, cloud infrastructure, mobile operators, banks, companies, governments, and eventually your screen. This is why geography still matters in the digital age. A country with more cable landings can become more connected, while a region with fewer routes can become more vulnerable. A city with strong cable access can become a data center hub. A country with weak international bandwidth can face slower internet and higher prices. That means undersea cables are not just technical infrastructure, they can shape economic opportunity. They affect education, outsourcing, remote work, cloud access, fintech, digital banking, AI, entertainment, and trade and services. A cable landing on a coast can quietly change the future of a country. But there is a darker side to this map. The same routes that connect the world can also reveal where the world is vulnerable. The internet looks decentralized, but in some places, it passes through narrow digital choke points that are much easier to disrupt than most people realize. Now imagine the work required to connect two continents. Before a cable is laid, engineers study the seabed. They look for underwater mountains, trenches, earthquake zones, fishing grounds, shipping lanes, volcanic areas, and places where anchors might drag. The route has to be planned carefully because the ocean floor is not flat. It is a dangerous landscape. Then comes the cable ship, a specialized vessel designed to carry thousands of kilometers of cable in giant tanks. These ships move slowly across the ocean, releasing the cable behind them with precision. Near the coast, where human activity is highest, the cable may be buried under the seabed using a sea plow or remotely operated equipment. Farther offshore, in deep ocean, the cable often rests directly on the seabed. This part is almost cinematic. A ship moving slowly across the ocean, a thin cable sliding into dark water, and a route being drawn across the planet. Once the cable is in place, it becomes part of the invisible architecture of civilization. But laying the cable is only the beginning. The cable has to survive fishing activity, anchors, earthquakes, underwater landslides, equipment failure, sabotage concerns, natural abrasion, and human mistakes. Cable damage is not rare. Around the world, submarine cables experience faults every year, often because of fishing activity, anchoring, or natural events. That sounds alarming, but the system is designed with redundancy. If one cable fails, traffic can often be rerouted through other cables. Most of the time, users never notice, but that depends on one thing: having enough alternative routes. When a region has many cables, the internet can bend around damage. But when a region depends on only a few routes, damage can become a national problem. And when a cable breaks, the repair process is not high-speed science fiction. It can involve something surprisingly old-fashioned: a ship, a hook, and a race against time. When a submarine cable fails, the internet does not repair itself by magic. A cable repair ship has to be sent. These ships are some of the most important vessels most people have never heard of. They locate the fault, travel to the area, and then retrieve the cable from the seabed. In many cases, crews use grappling tools to hook the cable and bring it to the surface. Think about that for a second. A piece of the global internet is pulled out of the ocean like a fishing line. Then specialists repair or replace the damaged section. Fiber strands have to be carefully spliced, the cable is tested, and then it is lowered back to the seabed. The process can take days or weeks, depending on location, weather, permits, depth, and availability of repair ships. This is one of the strangest truths of the modern world. Your AI tools, cloud storage, streaming platforms, stock markets, and international banking can depend on crews working at sea, sometimes in rough weather, repairing glass fibers by hand. The internet may be digital, but its survival can be very physical. And this creates a second problem. There are not unlimited repair ships. If multiple cables fail in the same region, or if a crisis affects a major route, repair capacity can become a bottleneck. The world may have built a digital civilization, but the maintenance system is still limited by ships, crews, ports, weather, and politics. Now the story moves from engineering into geopolitics. Because undersea cables are not just infrastructure, they are strategic targets. For a long time, submarine cables were seen mostly as telecom infrastructure, important but technical. That is changing. Today, undersea cables sit at the center of geopolitical anxiety. Governments worry about espionage. Companies worry about outages. Militaries worry about sabotage. Investors worry about resilience. And citizens worry when the internet suddenly slows down. The reason is obvious. A cable does not need to be destroyed to create disruption. It can be cut, damaged, tapped, threatened, or become too risky to repair quickly. This is why cable routes are increasingly strategic. A country that controls landing points has influence. A company that owns cable capacity has power. A region with many routes has resilience, while a region with few routes has vulnerability. In a world where data is money, power, intelligence, and military advantage, the cables carrying that data become part of national security. This is also why countries care about where cables land and who builds them. A cable route is not just a technical choice. It can be a political decision. Which countries does it pass near? Which companies operate it? Which landing stations does it use? Which governments can monitor, regulate, or influence it? The internet is often described as borderless, but under the ocean, the internet has geography, and geography has politics. But the biggest change may not come from governments. It may come from the companies building the next generation of cables, the tech giants. The old internet was built largely by telecom companies, but the new internet is increasingly shaped by hyperscalers like Meta, Google, Amazon, Microsoft, and other cloud and platform giants. Why? Because they need capacity. Every video upload, cloud backup, search query, AI prompt, enterprise software platform, and data center connection needs bandwidth. The more the world uses cloud computing and AI, the more these companies need their own high-capacity routes. This is why big tech is investing directly in undersea cables. That is not just an engineering project, it is a statement of power. The companies that build and control data routes can influence the speed, cost, and structure of the global internet. This does not mean they control everything, but it does mean the backbone of the internet is becoming more closely tied to the business models of the biggest technology companies in the world. Streaming needs cables. Cloud needs cables. AI needs cables. Global platforms need cables. And the next wave of the internet, AI assistance, real-time translation, cloud gaming, virtual worlds, remote work, automated logistics, and digital finance, will demand even more capacity. So the secret maze under the ocean is expanding. Not because people want prettier maps, but because the digital economy is hungry. But the more the world depends on these cables, the more one question becomes unavoidable. What happens when the maze breaks? Most cable failures do not create global chaos, and that is important to understand. The system has redundancy. Traffic can often reroute through other cables. Network operators constantly manage capacity, delays, and routing. But not every region has the same resilience. If several cables are cut near the same area, the consequences can become serious. Internet speeds can slow, cloud services can become less reliable, international calls can degrade, financial systems may face delays, businesses can lose connectivity, and countries can experience partial isolation from the global internet. This has happened in different forms in the past. Sometimes it happens because of ship anchors, sometimes because of fishing activity, sometimes because of earthquakes, and sometimes because of suspected sabotage or conflict-related incidents. The key point is that the internet is resilient, but not invincible. And resilience is uneven. A country connected by many diverse cables is safer than a country dependent on one or two routes. A region with multiple landing points is safer than a region where most traffic passes through a single vulnerable corridor. This is why cable diversity matters. It is not enough to have connection. You need alternative connection. The internet survives by rerouting, but rerouting only works if there is somewhere else for the data to go. And this leads to the deepest point of the story. The internet is not just a technology network. It is a trust network. Every time you open a website, you trust a chain of systems you never see. You trust your device, your Wi-Fi, your mobile network, your internet provider, data centers, cloud companies, submarine cables, landing stations, routing systems, power grids, and repair ships. The internet feels simple because all of this complexity is hidden. But hidden does not mean unimportant. In fact, the hidden parts may be the most important parts. Undersea cables are not just pipes for data. They are the physical proof that the digital world depends on old world infrastructure. Ships, ports, permits, seabed surveys, national security, insurance, engineering, maintenance, and geography all sit behind the internet we use every day. This is why the phrase, "the cloud," can be misleading. The cloud is not really a cloud. It is data centers connected by fiber, and much of that fiber crosses the ocean floor. So when people talk about the future, AI, global finance, remote work, streaming, automation, smart cities, they are really talking about a future that depends on the continued functioning of undersea infrastructure. The world stays connected because thousands of kilometers of cable remain intact, powered, repaired, protected, and upgraded. That is the quiet miracle. But it is also the quiet risk. Because the next time your video loads instantly, remember this. Somewhere beneath the ocean, a pulse of light may have crossed a cable that most of the world will never see. The story of undersea internet cables is really the story of modern life. We think the internet is wireless, but the world is connected by wires. We think the cloud is weightless, but it depends on land, power, buildings, ships, and glass fibers buried beneath the sea. We think digital life is separate from geography, but the internet still follows geography: coastlines, choke points, oceans, politics, and risk. This secret maze of undersea cables is one of the greatest engineering systems ever built. It connects markets, families, governments, companies, and almost every part of the modern economy. And most of the time, it works so well that we forget it exists. That may be the most impressive part. The global internet is not invisible because it is unreal. It is invisible because it is hidden in plain sight, beneath the ocean, carrying the modern world at the speed of light. If you want to understand the hidden systems that keep modern life running, follow the channel. More stories like this are coming next.